Have you ever looked up at the night sky and felt that deep, primal sense of wonder, that feeling that there's so much more happening out there than we could ever truly grasp? Right now, as you're watching this, the cosmos is alive with events so strange, so unbelievable, they almost sound like science fiction. Planets are being torn apart by invisible forces, stars are vanishing without a trace, and entire galaxies are engaged in a silent, violent dance that defies everything we thought we knew. This isn't something from the distant past or far future. It's unfolding in real time, right above our heads. Think about that for a second. At this very moment, telescopes around the world and in space are capturing mind-bending phenomena that challenge the very laws of physics. Black holes are devouring stars, sending out ripples in space-time. Unexplained radio bursts are flashing across the universe, messages from the void with no clear sender. And there are objects out there moving at impossible speeds, with origins so mysterious that even our brightest scientists are left speechless. These aren't just curiosities, they're active, ongoing mysteries that remind us how much we still have to learn. So what if I told you that you don't have to be an astrophysicist to witness these cosmic wonders? Today, we're going on a journey together, a tour of the 25 most bizarre events happening in the universe right now. We'll explore celestial bodies that behave in ways that shouldn't be possible, delve into forces that warp reality itself, and try to wrap our minds around discoveries so fresh, they're still being debated in observatories and research labs. This is your front row ticket to the greatest show the universe has to offer, and I promise by the end, you'll never look at the night sky the same way again. Our journey into the bizarre begins with a concept that is almost impossible to truly fathom: a whole lot of nothing. Not just the empty space between stars, but a region of the universe so profoundly, shockingly empty that it has been nicknamed the Great Nothing. This is the Boötes Void, and right now it is an active, expanding hole in the cosmic web. Picture our universe not as a random scattering of stars, but as a vast, intricate network, a cosmic spiderweb dotted with glittering galaxies. Now, imagine a tear in that web so enormous it could contain thousands of galaxies like our own Milky Way, yet inside there are barely any. The Boötes Void spans an almost incomprehensible 330 million light-years across. To put that in perspective, if you were to place our solar system at one edge of this void and travel at the speed of light, it would take you over 300 million years to reach the other side. And for nearly that entire journey, you would see nothing, darkness. A handful of lonely galaxies exist within this vast desert, isolated islands in an ocean of emptiness. This void isn't just a blank spot on a map. It's a real, physical structure whose existence challenges our understanding of how the universe formed after the Big Bang. So how does something like this even happen? Astronomers have two leading theories, and both are mind-bending in their own right. The first points to the very beginnings of everything. In the first fractions of a second after the Big Bang, the universe was a seething, chaotic soup of energy. Tiny quantum fluctuations, random ripples in this primordial density, were stretched to enormous sizes by a period of rapid inflation. The Boötes Void could be the ghost of one of these immense underdense ripples, a bubble that was mostly empty from the very start and just kept expanding as the universe grew around it. It's a fossil from the dawn of time. The second theory is admittedly more speculative but far more thrilling. Some have wondered if such a colossal void could be evidence of a Type 3 civilization on the Kardashev scale, a civilization so advanced it has harnessed the energy of entire galaxies. The hypothesis suggests they might have constructed a Dyson sphere, or rather, a Dyson swarm, around not just one star, but every star in a vast region of space, blocking their light from view and making the area appear dark and empty to our telescopes. While this is a fascinating thought experiment, most scientists consider it extremely unlikely. as it would require a coordination and energy manipulation on a scale we can barely imagine. The simpler explanation of primordial fluctuations is usually favored, but the mystery is what keeps us looking, and we are looking with more powerful tools than ever before. New generations of radio telescopes, like the upcoming square-kilometer array, are now turning their gaze toward the void. They aren't just looking for the absence of light, they are listening. They are searching for the faintest whispers of hydrogen gas, the building blocks of galaxies, hoping to map the true structure of this emptiness in real time. By studying the distribution of the few galaxies that do call the void home and analyzing the faint echo of the cosmic microwave background radiation that passes through it, astronomers are essentially taking an X-ray of this cosmic anomaly, trying to diagnose what caused this great wound in the fabric of the cosmos. But our next cosmic mystery pulls us from a vast emptiness to a single, specific point of light, one that has been behaving so strangely it has sparked one of the biggest astronomical debates of our time. This is Tabby's star, officially catalogued as KIC 8462852, and right now, as you hear this, its light is reaching Earth after a 1,200-year journey, carrying with it a signal so bizarre that it simply doesn't make sense. Located in the constellation Cygnus, this otherwise ordinary star is doing something no other star we've observed has ever done. It is dimming in dramatic, unpredictable, and utterly inexplicable ways. The story begins with the Kepler Space Telescope, which was designed to hunt for planets by staring at stars and waiting for the tiny, periodic dips in brightness caused by a world passing in front of them. Kepler saw what it was looking for thousands of times over, but it also saw something it wasn't programmed to find. The light from Tabby's star didn't dip in a clean, repeating pattern. Instead, it plummeted. At one point, the star's light output dropped by a staggering 22%. To understand how massive that is, consider that even a giant planet like Jupiter would only block about 1% of a sun-like star's light when it transits. A 22% dimming suggests something colossal is passing in front of this star, something with a surface area many times larger than the star itself. And these dips aren't neat and tidy, they are asymmetric with sharp declines and more gradual brightening, lasting for days or even weeks at a time. It's a light curve that looks less like an orbit and more like a chaotic scramble. Naturally, the quest for an explanation began, and the theories range from the natural to the extraordinary. The leading natural hypothesis involves a massive swarm of comets. The idea is that a family of exocomets, perhaps disturbed by the gravity of a nearby star, could be breaking apart and creating an enormous, dense cloud of dust and debris that intermittently blocks the star's light. This could account for the irregularity and the depth of the dimming. Another compelling idea points to dust from a catastrophic planetary collision, a cosmic crash of unimaginable scale that left a ring of fine particles circling the star, occasionally clumping together to blot out its glow. Some have even proposed that the star itself might be undergoing internal processes we don't yet understand, though no known stellar behavior can account for such extreme and sporadic changes. Then, of course, there is the more speculative possibility that has captured the public's imagination, the alien megastructure hypothesis. The idea, first suggested by astronomer Jason Wright, is that what we might be witnessing is a partially constructed Dyson swarm, a vast collection of energy collecting satellites or platforms built by an advanced civilization to harness the entire power output of their star. This wouldn't be a solid shell, but a dense, uneven array of objects that would cause exactly the kind of irregular, deep dimming patterns we observe. While scientists are quick to point out that this is the least likely explanation, it remains on the table simply because every natural cause proposed so far has run into significant problems. Comet swarms, for instance, would likely require more comets than could possibly exist in that solar system, and the fine dust involved should glow in infrared light, which we don't see in the amounts we'd expect. So the mystery deepens and the monitoring intensifies. Right now, telescopes across the globe, from amateur backyard setups to massive professional observatories, are keeping a constant watch on Tabby's star through initiatives like the Tabby Star Observing Campaign. Every time it dips, an alert goes out, and the world turns its eyes to Cygnus, collecting spectra, measuring light, and searching for any clue in the data. With each observation, we learn a little more. We've seen that the dimming affects some colors of light more than others, which strongly suggests we're dealing with ordinary dust particles that are fine like smoke, not solid megastructures. This has made the comet or collision dust ring theory the current frontrunner, but the question is far from settled. The sheer scale and strangeness of the event means we are still watching a cosmic detective story unfold in real time, a reminder that the universe is always ready to surprise us. Leaving behind the visual puzzle of a flickering star, we now turn to a mystery that arrived not as a slow, dimming light, but as a single, deafening shout in the silent cosmos. It lasted for just 72 seconds, but its echo has persisted for decades, captivating astronomers and fueling our deepest curiosities about who or what might be out there. This is the WOW signal, and the hunt for its source is more active today than ever before. It was August 15, 1977, at the Big Ear Radio Telescope in Ohio. Volunteer Jerry Amon was methodically scanning reams of data printouts, the kind with columns of letters and numbers representing signal strength. The telescope was pointed toward a group of stars in the constellation Sagittarius, listening to the universe on a frequency near 1420 MHz. This frequency is in a uniquely quiet band, a protected water hole where cosmic static is minimal, and which many scientists speculate would be a logical channel for interstellar communication. That night, the telescope's receiver recorded a signal so intense, so perfectly aligned with this ideal frequency, that it defied all natural explanation. When Amon saw the alphanumeric sequence on the printout 6 equals UJQ, he circled it and simply wrote WOW in the margin, giving the signal its immortal name. It was a burst of pure power, and then it was gone. For over 40 years, that single data point was all we had. Countless attempts to detect a repeat signal from the same spot came up empty. It was a cosmic one-hit wonder, but the mystery refused to die because the signal's profile was so bizarrely artificial. It wasn't a wide, messy blast of noise. It was a narrowband signal, meaning it was focused on one very specific frequency, much like a radio station you tune into on your dial. It also exhibited a telltale rise and fall in intensity over the 72 seconds, exactly what you'd expect as the rotation of the Earth slowly carried the Big Ear telescope's field of view across a stationary source in the sky. It fit the profile of a signal of intelligent origin perfectly. This brings us to the present day, where modern technology is finally allowing us to investigate this cold case with new tools. The primary target is a Sun-like star known as 2 mass 1928198233000097, located almost exactly in the center of the two potential regions where the Big Ear was pointing. Using powerful arrays like the Very Large Array in New Mexico and the Allen Telescope Array in California, which is specifically designed for the search for extraterrestrial intelligence, astronomers are now conducting deep, sustained scans of this area. They are no longer limited to a single frequency. They can monitor millions of channels simultaneously with a sensitivity that the Big Ear operators in the 1970s could only dream of. They are looking for any whisper of a repeat transmission or even a fainter, continuous signal the original telescope might have missed. So what could it have been if not a message? The leading natural explanations are just as fascinating. One possibility is that the signal was caused by a comet. In 2016, an astronomer proposed that two comets, 266P Christensen and 335P Gibbs, which were in the vicinity at the time, could have been the culprits. Comets are surrounded by massive clouds of hydrogen gas, which can emit strong signals at the exact frequency the WOW signal was detected. However, this hypothesis has been heavily debated, with other scientists checking orbital records and arguing that those specific comets were not actually in the telescope's beam at that precise moment. Another idea points to a phenomenon called gravitational lensing, where the gravity of a distant object bends and amplifies a random radio wave from much farther away, creating a temporary bright flash that would never repeat. Yet the possibility that it was something more remains, hanging in the air like a tantalizing scent. The renewed investigation is not just about solving a historical puzzle, it's a test of our entire approach to searching for intelligence beyond Earth. The WOW signal taught us that the universe might not be filled with constant, obvious broadcasts, but with brief, sporadic bursts. It's the ultimate lesson in cosmic patience and persistence. Right now, as we analyze new data from that patch of sky, we are poised for a possibility that is both thrilling and humbling, that the phone rang once 47 years ago, and we are only now lifting the receiver to our ear, listening intently for the faintest hint of a voice saying hello once more. But if the WOW signal was a single, unexplained shout, then what we're about to discuss is an entire symphony of cosmic screams, repeating in rhythms so complex and puzzling they have astronomers questioning the very nature of reality itself. These are fast radio bursts, or FRBs, and the discovery that some of them are not just random, but are transmitting in intricate, repeating patterns, has thrown the field of astrophysics into a thrilling and profound state of bewilderment. Imagine for a moment a flash of energy so powerful it can outshine an entire galaxy, but a flash that lasts for less time than it takes to blink your eye. That is an FRB. For years after their initial discovery, these events were thought to be one-off cataclysms, the final, dying screams of stars being vaporized or neutron stars colliding in unimaginable explosions. The universe, it seemed, was filled with these random, ultra-brief fireflies popping in and out of existence. But then everything changed. We found one that didn't just flash once, it flashed again. And again and again, we had found a repeater. This alone was a monumental discovery, suggesting that whatever was causing these bursts wasn't always destroyed in the process. But the real shock was yet to come. As we listened to more of these repeating FRBs, we began to detect something even more bizarre hidden within the noise patterns. Not just simple, periodic repetitions, but complex, ticking clock sequences that cycle over days. One of the most famous, FRB 180916, was found to have a pattern where it would erupt violently for roughly 4 days, then fall completely silent for 12 days before starting the entire 16-day cycle over again. It's a schedule, a timetable written on a cosmic scale. Another, FRB 121102, exhibits a more nuanced 157-day cycle of activity and quiet. This isn't the behavior of a random, chaotic explosion. This is the behavior of a mechanism. It's as if we're listening to a natural, cosmic lighthouse, its beam sweeping across the universe with a terrifying and regular precision. The immediate, spine-tingling question is, what kind of natural clock could possibly keep time on such a scale? The hunt for answers is a global, real-time endeavor unlike any other in astronomy. Because these bursts are so fleeting, lasting mere milliseconds, catching them requires a coordinated worldwide network of telescopes. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a powerhouse in this field, its unique design allowing it to stare at a huge swath of sky constantly, acting as a permanent listening post for these cosmic ticks. But when CHIME detects a burst, it instantly sends out an alert, a cosmic bat signal to observatories all over the world and in space. Within seconds, the Neil Gehrels Swift Observatory, the Hubble Space Telescope, and massive radio dishes from Chile to China all swivel to pinpoint the source galaxy, trying to capture any other wavelength of light, X-ray, optical, infrared, that might be associated with the event. This is astronomy at the speed of light, a frantic race to decode a message that vanishes almost the instant it arrives. So what is creating these patterned screams? The natural explanations are as fascinating as they are varied. The prime suspect is a type of neutron star called a magnetar. These are the universe's ultimate magnets, stellar corpses with magnetic fields so powerful they could erase a credit card from halfway to the moon. One theory suggests that the complex patterns could be caused by the precession of a magnetar, a slow, wobbling rotation of its axis, much like a spinning top winding down. As it wobbles, a particularly active crack on its solid, crusty surface might only point toward Earth at specific intervals in its cycle, creating the observed pattern of activity and silence. Another idea involves a magnetar in a binary orbit with another star. The intense gravitational tides and wind from its companion could periodically trigger quakes on the magnetar's surface, unleashing the bursts on a strict orbital schedule. Yet the precision and complexity of these patterns inevitably lead some to ponder a more extraordinary possibility. Could this be a sign of intelligence? The notion is not that the bursts themselves are an encoded message, but that they could be a byproduct of unimaginably advanced technology. A proposed, though highly speculative, idea is that of an interstellar light sail, a spacecraft powered not by fuel, but by the momentum of light beams from a powerful transmitter on a planet. If such a transmitter were to be sweeping across the sky to propel a craft, its beam might periodically wash over Earth, appearing to us as a repeating, highly energetic burst. It's a thought that pushes the boundaries of science into the realm of wonder, a reminder that in a universe this vast, we must, as Carl Sagan said, keep our minds open to extraordinary possibilities. The truth is, we simply do not know yet. The beauty of this mystery is that it is actively unfolding. With every new patterned FRB we discover, with every multi-wavelength observation made in those critical milliseconds after an alert, we gather another piece of the puzzle. We are, in a very real sense, learning to read the rhythms of the cosmos, listening to the regular heartbeat of phenomena we are only beginning to understand. It is a detective story written in milliseconds and megaparsecs, and right now, we are all on the edge of our seats, waiting for the next clue to arrive from the darkness. But our tour of cosmic oddities would be incomplete without revisiting one of the most controversial visitors to ever grace our celestial neighborhood, an object that sparked a debate which continues to rage in scientific journals and conference halls to this day. This is Oumuamua, the first known interstellar object to pass through our solar system, and its mysterious journey is far from over. Right now, this silent, enigmatic traveler is continuing its voyage into the black, beyond the orbit of Neptune, and as it speeds away from us at over 100,000 miles per hour, it is taking its secrets with it, leaving us with more questions than answers about what exactly we witnessed back in 2017. When the Pan-STAR 1 telescope in Hawaii first spotted it, Oumuamua was already on its way out, having already made its closest approach to the Sun. This meant we had an incredibly short and frantic window to observe it. The initial data was baffling. It didn't look or behave like any asteroid or comet we had ever seen. First, its shape was utterly bizarre. Based on the extreme variations in its brightness as it tumbled through space, astronomers deduced it was highly elongated, perhaps 10 times longer than it was wide, a shape like a cosmic cigar or a pancake. This is an extremely unusual configuration for a natural space rock, which tend to be more lumpy and rounded. Second, and most puzzling of all, was its acceleration. As it hurtled away from the Sun, something was giving it an extra push. A comet's acceleration is typically explained by outgassing. The Sun's heat vaporizes ice on its surface, creating jets of gas that act like a natural thruster. But Oumuamua showed no visible signs of this activity, no coma of gas and dust, no tail streaming behind it. It was accelerating as if it were a comet, but it looked utterly like a silent, dormant asteroid. This is the core of the mystery that continues to divide the scientific community. One camp, led by astronomers like Dr. Karen Meach, who led the initial characterization team, argues for a natural explanation, albeit a rare one. Their compelling theory suggests Oumuamua could be a fractal-like chunk of nitrogen ice. Imagine a body that began as part of a Pluto-like planet in another star system. A colossal impact could have shattered its surface, ejecting a shard of pure nitrogen ice into the void. As this iceberg traveled through the cold of interstellar space, it would have been eroded by cosmic radiation, sculpting it into that strange, flattened shape. Then, when it approached our sun, the heat would have caused the nitrogen to sublimate, to turn directly from a solid into a gas, providing the precise non-gravitational push we observed, all without creating the dusty coma typical of water-ice comets. It would be an entirely new class of object, a relic from the construction of an alien solar system, and its discovery would be a landmark moment in astronomy. The other perspective, most famously put forward by Harvard astronomer Professor Avi Loeb, posits that the object's peculiarities could be evidence of a technology not of this world. Loeb argues that the most straightforward explanation for the extra acceleration is solar radiation pressure, the idea that sunlight itself was pushing on the object. For this to work, Oumuamua would need to be extremely thin and lightweight, with a large surface area and very low mass, a sail. This leads to the extraordinary suggestion that we might have witnessed a piece of advanced technology, a light sail floating through the galaxy, perhaps as debris from a long-gone civilization or a functional probe that has long since ceased to operate. While this idea is treated with extreme skepticism by the majority of the astronomical community, Loeb and his supporters maintain that we must not dismiss the possibility simply because it seems extraordinary, especially when the natural explanations require us to invoke objects we have never seen before. So where is Oumuamua now, and can we ever get answers? Currently, it is sailing through the Kuiper belt, far too faint and distant for any current telescope, including Hubble or the James Webb, to observe. It is truly gone from our sight. However, the debate it sparked has fueled a new era of vigilance. Because of Oumuamua, we are now actively hunting for other interstellar visitors. This effort has already paid off with the detection of a second object, 2I Borisov, which behaved exactly like a predictable, icy comet, complete with a magnificent tail. Its normalcy only made Oumuamua seem more peculiar by comparison. The upcoming Vera C. Rubin Observatory, with its unprecedented ability to scan the entire visible sky every few nights, is poised to find many more of these visitors, perhaps even catching them on their way in, giving us years instead of weeks to study them. Oumuamua's legacy is not a solved mystery, but a revolution in our perspective. It taught us that our solar system is not an isolated island, but a dynamic crossroads occasionally visited by debris from other stars. It forced us to question our assumptions and to consider that the universe might be filled with phenomena we haven't even begun to categorize. Whether it was a nitrogen iceberg or a fragment of a long-dead sail, its brief, silent passage changed astronomy forever, a reminder that sometimes the most profound discoveries are the ones that leave us quite literally in the dark. Yet while Oumuamua represents a singular, fleeting mystery, the next cosmic puzzle we're about to explore is both vast and fundamental, woven into the very fabric of the cosmos itself. It concerns a substance that is everywhere and yet nowhere, an invisible scaffold that holds the universe together yet refuses to be seen. We are talking, of course, about dark matter, and right now, our most powerful telescopes are capturing something deeply unsettling. This hidden material is not behaving the way our most cherished models of the universe say it should. It is clumping together in ways that defy prediction, creating a cosmic contradiction that is playing out in real time across the sky. To understand why this is so bizarre, we first need to grasp the standard model of cosmology, often called the lambda cold dark matter model. This is the established playbook for how our universe works. It posits that dark matter is cold, meaning its particles move relatively slowly. This sluggishness allows it to clump together under gravity, forming an immense, invisible cosmic web. This web serves as the framework upon which ordinary, visible matter, the gas and dust that make up stars and galaxies, can gather. For decades, this model has been spectacularly successful, accurately predicting the large-scale structure of the universe and the patterns we see in the cosmic microwave background. But now, by using nature's own magnifying glass, we are peering at the finer details of this web and finding cracks in the foundation. The primary tool for this investigation is gravitational lensing, one of the most elegant and powerful predictions of Einstein's theory of general relativity. The concept is that massive objects like galaxy clusters warp the fabric of space-time around them. This warping acts like a lens, bending and distorting the light from galaxies that lie far behind them. By meticulously studying this distortion, astronomers can create a map of the lens's mass, including both its visible stars and, most importantly, its invisible dark matter halo. It's a way of taking an X-ray of the cosmos, revealing the skeleton that lies beneath the skin. Teams using the Hubble Space Telescope and, more recently, the James Webb Space Telescope are conducting these precise measurements, and the results are not matching our simulations. The discrepancies are appearing in specific, well-studied clusters. Take Able 521, for instance. This colossal collision of galaxies, located over 2 billion light-years away, is a natural laboratory for dark matter. By mapping its mass distribution through lensing, astronomers found that the dark matter is clumped together much more densely and in a different configuration than computer models predicted. Similar anomalies are being recorded in other clusters, like the famous El Gordo cluster. The dark matter seems to be clinging to itself in ways that the cold dark matter model doesn't easily account for. It's as if we've learned the rules of a game, only to watch the players on the field consistently breaking them in small but significant ways. So what could be causing this unexpected clumping? The theories being debated in observatories right now are as thrilling as they are profound. One possibility is that dark matter isn't as cold as we thought. Perhaps some component of it is warm, meaning its particles are moving at a significant fraction of the speed of light. This slight warmth would prevent it from collapsing into the very finest, densest clumps, smoothing out the distribution in a way that might better match these new, real-world observations. Another, more radical idea is that dark matter possesses a unique property beyond just gravity. Perhaps it can interact with itself through a mysterious force, a kind of dark light or dark electromagnetism that allows it to collide and stick together, enhancing its ability to form these puzzling, dense cores. The implications of these discoveries are staggering. If the standard model requires a fundamental revision, it means we have to rethink the entire history and fate of the universe. The rate at which galaxies formed, the very timeline of cosmic evolution, is dictated by the behavior of dark matter. Furthermore, these lensing studies are no longer historical artifacts. They are active, ongoing observations. The James Webb Space Telescope is right now collecting data on distant lensing clusters with unprecedented resolution and new sky surveys like the one planned with the Vera C. Rubin Observatory will provide statistical samples of millions of lenses, moving us from a few puzzling case studies to a comprehensive understanding of the problem. We are witnessing the first tremors of a potential revolution in physics, a shift in our comprehension of the universe's most basic ingredients, all revealed by the subtle warping of light from the distant universe. Even as we grapple with the invisible architecture of dark matter, there is a force at work on an even grander scale, a cosmic tug so powerful it is pulling our entire galaxy and thousands of others on a relentless journey we cannot see the end of. This is the mystery of the Great Attractor, a gravitational anomaly of such immense power that it defies both our view and, for a long time, our understanding. Right now, the Milky Way, along with our entire local group of galaxies, is being hauled through space at an astonishing 14 million miles per hour toward a point in the constellation Centaurus, pulled by a source we are still struggling to reveal. For decades, the true nature of this force was one of astronomy's most frustrating puzzles, primarily because it lies in a direction that is effectively hidden from our view. This region is known as the Zone of Avoidance, a poetic name for a practical problem, the dusty, star-choked plain of our own Milky Way galaxy. It's like trying to see a distant mountain range through a thick, persistent fog. Our optical telescopes were completely blind to what lay beyond this veil of gas and dust. The Great Attractor wasn't just mysterious, it was literally invisible. The breakthrough came when we stopped trying to see with visible light and started to listen with other parts of the electromagnetic spectrum. Infrared telescopes like NAS, a wide-field infrared survey explorer, could peer through the obscuring dust, seeing the heat glow of stars and galaxies hidden behind it. Even more revealing were X-ray observatories, like the Chandra X-ray Observatory and the European Space Agency's XMM Newton. Where there is a massive concentration of galaxies, there is also incredibly hot gas that emits X-rays. By mapping these X-ray sources, astronomers could finally begin to trace the outline of the colossal structures lurking in the zone of avoidance. What they found was not a single monolithic object, but something far more complex and grand. We now understand that the Great Attractor is not a lone, super-dense monster, but rather the core of a much larger cosmic structure, the heart of what we call the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is our galactic continent, a vast filamentary network of over 100,000 galaxies, all bound together by gravity and all flowing toward the same gravitational center. The Great Attractor is the central gravitational valley of this supercluster, the point of lowest gravitational potential where everything is naturally draining. Our Milky Way is like a leaf caught in the current of a river, flowing toward a waterfall we are only beginning to map, but the story doesn't end there. The pull we feel is not just from Laniakea. Recent mapping efforts suggest an even larger and more massive structure lies beyond it, acting as an ultimate anchor in the cosmic flow. This is the Shapley supercluster, a staggering concentration of mass containing dozens of massive galaxy clusters. It is one of the most massive structures in the observable universe, and its immense gravity is influencing the motion of Laniakea itself, and by extension, us. So our journey is a layered one. We are being pulled toward the Great Attractor, which is itself being pulled toward Shapley, in a cosmic hierarchy of gravity that spans hundreds of millions of light years. The effort to fully map this invisible landscape is ongoing and more sophisticated than ever. Projects like the Cosmic Flows Survey are meticulously measuring the precise velocities of thousands of galaxies, using them to reverse engineer the distribution of mass in the universe and create a three-dimensional map of our extended cosmic neighborhood. Each new data point adds detail to this chart of the unknown, slowly pulling back the curtain on the forces that have shaped our galactic destiny for billions of years. The Great Attractor, once a profound mystery, is now a focal point of discovery, a reminder that even when the universe hides its greatest wonders, our curiosity and ingenuity will always find a way to bring them into the light. Yet even as we chart the grand structures pulling our galaxy, we are simultaneously discovering that the vast spaces between the stars are not as empty as we once believed. They are haunted, drifting through the immense, lightless voids are countless worlds untethered to any sun, cast out from their home systems and condemned to an eternal night. These are rogue planets, and right now, our ability to detect these dark, nomadic worlds is exploding, revealing a hidden population that may outnumber the stars themselves. The challenge in finding these objects is monumental. Unlike planets orbiting a star, which we can detect by the slight dimming they cause as they transit or the wobble they induce in their host star, rogue planets give off no light of their own and have no star to betray their presence. They are, for all intents and purposes, invisible. To find them, astronomers rely on one of Einstein's most fascinating predictions, that a massive object can warp spacetime enough to act as a lens, briefly magnifying the light of a star far behind it. This phenomenon is called gravitational microlensing. Imagine a rogue planet drifting silently through the galaxy. For a fleeting moment, its gravity will bend and focus the light from a distant background star. To us, that star will appear to temporarily brighten in a very specific, predictable way, a flash in the dark that can last from a few hours to a couple of days. It is an incredibly rare and precise alignment, a cosmic blink and you miss it event that requires constant, vigilant monitoring of millions of stars to catch. This is precisely what's happening right now on a global scale. Projects like the Optical Gravitational Lensing Experiment, or OGLE, based in Chile, and Korea's Microlensing Telescope Network, are engaged in a relentless, automated survey of the dense star fields toward the center of our galaxy. Night after night, their telescopes capture countless images, feeding them into sophisticated software algorithms that scan for the telltale signature of a microlensing event. When one is detected, an alert is sent out to a worldwide network of astronomers who then train other telescopes on the event to confirm it and gather precious data on its light curve. This real-time, coordinated effort is how we are building a census of these invisible wanderers, and the numbers are staggering. Current estimates suggest there could be hundreds of billions of these rogue planets in the Milky Way alone, a population of orphans far exceeding the number of stars that light our sky. What does this immense population of lonely worlds tell us? For planetary scientists, it is a revolutionary window into the often violent and chaotic process of planetary formation. The leading theory is that most of these planets were not born in darkness, but were violently ejected from their young solar systems during the turbulent early days when giant planets were jostling for position. Their gravitational interactions slingshotted smaller, Earth-sized worlds out into the interstellar deep. The sheer number of these rogues we are finding suggests that this ejection process is not a rare anomaly, but a fundamental and common part of how planetary systems are built. Our own solar system may have once had more planets that were cast out into the void long ago, a ghostly retinue forever lost to the sun's gravity. This naturally leads to one of the most captivating questions in all of astronomy. Could any of these dark, frozen worlds harbor life? The conventional definition of a habitable zone requires a star to provide warmth and energy. A rogue planet, by its very nature, has none of that. Its surface would be a global deep freeze, with temperatures plunging hundreds of degrees below zero. Yet, life is tenacious and our understanding of its requirements is evolving. If a rogue planet has a thick hydrogen atmosphere, it could act as an insulating blanket, trapping residual heat from the planet's formation and radioactive decay in its core. This could maintain a subsurface ocean of liquid water, much like those suspected to exist on moons like Europa and Enceladus, but on a planetary scale. In the absolute blackness between stars, the only energy would be geothermal, welling up from the planet's interior. An ecosystem in such a place would be utterly alien, perhaps based on chemosynthesis rather than photosynthesis, existing in a warm, dark sea beneath a permanent, icy sky and an eternal canopy of stars. It is a profoundly lonely thought that life could exist in such complete isolation, traveling through the galaxy on a journey with no destination and no end. But our attention now turns from the wandering orphans of the cosmos to a star that feels far more familiar, a constant sentinel in our winter sky that recently decided to behave in a way that has the entire astronomical community watching with bated breath. This is Betelgeuse, the brilliant red supergiant marking the shoulder of the constellation Orion. And its recent dramatic dimming event was not a one-time spectacle, but the beginning of an ongoing, captivating mystery that is still unfolding in real time. Right now, as you look up at that familiar orange-red point of light, it is pulsating and changing in ways we are still striving to understand, and its ultimate fate could deliver one of the most spectacular celestial events in human history. The story captured global attention in late 2019. Betelgeuse, one of the brightest stars in our sky, began to fade. This wasn't a subtle shift. It was a dramatic plunge in brightness, dimming by over 60% at its lowest point, a change so significant it was visible to the naked eye. The familiar shoulder of Orion seemed to vanish, a sight that sparked both public fascination and scientific urgency. Was this the final act? Was Betelgeuse, a star known to be near the end of its life, about to explode in a glorious supernova? The event, now known as the Great Dimming, became a global observing campaign with every available telescope, from backyard instruments to the Hubble Space Telescope, turning its gaze toward Orion. As the data poured in, a clearer, though no less fascinating, picture began to emerge. The star did not explode. Instead, it slowly recovered its brightness over the following months. But the event left behind a trail of clues that astronomers are still piecing together. The leading explanation is a spectacular one-two punch of stellar phenomena. First, immense cool spots, similar to sunspots but on a colossal scale, developed on the star's surface. These are not mere blemishes. We are talking about magnetic disturbances so vast they could cover a significant portion of the star's southern hemisphere, regions that are cooler and therefore dimmer than the rest of the turbulent surface. This drop in surface temperature alone would cause a noticeable dimming from our vantage point, but that was only half the story. Data from Hubble suggested that simultaneously, the star likely belched out an enormous cloud of superheated gas and dust. As this material drifted away from the star and cooled, it condensed into what was essentially a cosmic veil of stardust, partially blocking our view and compounding the dimming effect. We weren't just watching a star grow faint, we were witnessing a titanic, real-time eruption and the creation of a temporary stellar shade. This combination of a cooler surface and a dust cloud now stands as the most compelling natural explanation for the Great Dimming, a testament to the dynamic and violent processes at work in these aging stellar giants. Yet, the mystery is far from solved because Betelgeuse's strange behavior did not end with its recovery. The star continues to pulsate and flicker in ways that defy its previously established 400-day cycle. It is a variable star, meaning its brightness naturally rises and falls as its massive body expands and contracts, breathing in a slow, cosmic rhythm. But its pulse has become irregular, almost arrhythmic. Current observations show it cycling through periods of unusual brightness and subsequent dimming on a much faster and more erratic timetable than ever recorded before. This has led to a resurgence of the more profound, ultimate question. Are we watching the final, unstable years of a star on the verge of death? The possibility that Betelgeuse could go supernova within our lifetimes is a thrilling one, and it is this potential that fuels such intense and continuous study. Located a comparatively close 640 light-years away, a Betelgeuse supernova would be a daytime event. It would shine as brightly as a full moon for several weeks, casting shadows on the ground at night and remaining visible to the naked eye for over a year. It would be utterly harmless to life on Earth, but it would be the most significant stellar event witnessed by human civilization in recorded history, a front-row seat to the cosmic death of a giant. The energy released would provide an unprecedented laboratory for studying neutrino physics, the formation of heavy elements, and the birth of a new nebula that will one day form new stars and planets. This is why the monitoring continues with such fervor. Instruments like the Hubble and James Webb Space Telescopes are analyzing its surface in incredible detail, searching for signs of further instability. Ground-based observatories using advanced interferometry are actually resolving the disk of the star itself, watching for changes in its shape and the development of new, giant convective cells that bubble up from its interior like boiling cauldrons. Every flicker, every slight dimming is catalogued and analyzed. We are, in a very real sense, taking the pulse of a dying star, waiting for the moment its heart finally gives out. Whether that moment comes tomorrow or in 100,000 years, the ongoing saga of Betelgeuse's dimming has given us a profound glimpse into the final, tumultuous chapters of a star's life. A powerful reminder that even the most constant fixtures in our sky are capable of breathtaking and unpredictable change. Yet, even as we discover countless worlds that could potentially cradle life, we are met with a profound and unsettling silence. This contradiction is the heart of the Fermi paradox, the famous question first posed by physicist Enrico Fermi. If the universe is so vast and ancient, and the ingredients for life seem so common, then where is everybody? Right now, this paradox is not a static philosophical puzzle. It is an active, deepening mystery, made more intense by a flood of new data that simultaneously increases the odds of life's existence and underscores the eerie quiet from the stars. The first pillar of this modern paradox is the absolute revolution in exoplanet discovery. Missions like NASA Kepler and TESS have transformed our understanding of planetary systems. We now know that planets are not the exception but the rule. The current statistics are staggering. Data suggests there are more planets in our galaxy than there are stars, with billions of those orbiting within their star's habitable zone. That Goldilocks region where temperatures could allow for liquid water to exist on a rocky surface. We have moved from wondering if other Earths exist to knowing they are incredibly common. The universe appears to be teeming with real estate that looks from a distance perfectly suitable for life. This expansive new reality makes the subsequent silence not just puzzling but deafening. This is where the search for extraterrestrial intelligence, or SETI, enters its most sophisticated era. The effort is no longer about a single large dish listening for a powerful, deliberate broadcast. Modern SETI is a multifaceted, data-driven endeavor that leverages the world's most powerful radio telescopes like the Allen Telescope Array and even optical telescopes searching for laser pulses. But the real game changer is happening in the algorithms. Scientists are now employing advanced machine learning and artificial intelligence to sift through the monumental amounts of data collected. These AI systems can analyze signals with a speed and nuance impossible for humans, filtering out terrestrial interference like satellite transmissions and natural astrophysical phenomena to isolate a potential candidate that exhibits the hallmarks of an artificial, technological origin, a signal that is narrowband, drifting in frequency due to a planet's motion, or originating from a system known to host exoplanets. Furthermore, the search parameters have expanded dramatically. We are no longer just listening for a simple hello. Initiatives like Breakthrough Listen are now searching for what are called technosignatures, a broader evidence of technology that could be detected across interstellar distances. This could include the chemical signatures of industrial pollution in an exoplanet's atmosphere, the waste heat from a hypothetical Dyson sphere megastructure, or even the light sail signatures of giant spacecraft. The search has become holistic, scanning the cosmos for any sign of a technological footprint, however faint or unintended it might be. And with every passing day, the volume of space we have searched and the sensitivity of our instruments grows exponentially. And yet, the result so far is a profound nothing. This great silence is what makes the Fermi paradox a bizarre event happening in the present moment. It's not a historical question, it's a real-time observation. Every minute that passes without a detection adds another day to point to the mystery. This lack of evidence forces us to confront a number of sobering and sometimes frightening possibilities known as the Great Filters. The idea is that there may be an evolutionary hurdle so difficult that almost no civilization surpasses it. This filter could lie in our past. Perhaps the emergence of life itself is astronomically rare. Or, more worryingly, it could lie in our future. perhaps every advanced civilization eventually discovers the technology for self-destruction, whether through nuclear war, environmental collapse, or a runaway artificial intelligence, and that is the silence we are hearing. Another possibility is that we are simply too early or too late to the cosmic conversation, that intelligent civilizations are separated by such vast gulfs of time that overlap is exceedingly rare. There are less ominous solutions, of course. Perhaps spacefaring civilizations are common, but they utilize communication technologies so advanced and efficient that their signals are undetectable to our primitive instruments using neutrino beams or quantum entanglement in ways we cannot yet fathom. Or maybe the universe is simply too big. Their signals have not reached us yet, or our own brief century of radio transmission is still far too small a bubble in the galaxy to have been noticed. The truth is, we do not know. The ongoing, active search for an answer to the Fermi paradox is one of the most profound scientific endeavors of our time. It is a real-time experiment testing our place in the universe, and with every new exoplanet discovered and every silent hour of observation, the paradox only deepens, challenging our optimism and our fears about what might be waiting for us in the dark. But while the search for life confronts us with a vast and puzzling silence, the very fabric of space itself is anything but quiet. At the smallest imaginable scales, a seething, bubbling ocean of energy is constantly coming into and out of existence, a chaotic dance that may hold the key to the universe's greatest mysteries. This is the quantum vacuum, and right now, in highly specialized laboratories around the world, physicists are running experiments to directly probe this mysterious quantum foam for the very first time. To understand what this means, we have to rethink our idea of nothing. We often imagine the vacuum of space as a true void, a perfect and utter emptiness. But according to quantum mechanics, this is a profound illusion. At the quantum level, empty space is a turbulent sea of virtual particles. Pairs of particles and antiparticles spontaneously pop into existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating each other and vanishing back into the void. This isn't just theoretical, it's a verified phenomenon with real-world effects we can observe, like the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum are gently pushed toward each other by the pressure of these virtual particles fluctuating outside them. The challenge and the focus of cutting-edge research today is moving from observing the side effects of this vacuum energy to directly measuring its properties. One of the most ambitious efforts involves using incredibly precise lasers and mirrors. The idea is to fire a laser beam into a device called an interferometer, which splits the light and sends it down two perpendicular arms before recombining it. If the vacuum fluctuations are real, they should create a subtle, random jitter in the mirrors at the ends of these arms, a minuscule shaking that would slightly alter the path length of the light and create a detectable signal in the recombined beam. The level of precision required is almost beyond comprehension. We're talking about measuring movements smaller than the diameter of a proton. Experiments like the Fermilab holometer are dedicated to this very task, acting as ultra-sensitive microphones trying to hear the faint hiss of spacetime itself. Other researchers are approaching the problem from a different angle, using powerful magnetic fields to try and manipulate the vacuum. In principles based on quantum electrodynamics, a strong enough magnetic field should affect the polarization of light traveling through a vacuum, subtly twisting it in a phenomenon known as vacuum magnetic birefringence. Experiments like the Pavlov's experiment in Italy are attempting to create these powerful fields and measure this extremely faint effect. It's like trying to detect how a vast, powerful magnet might bend a beam of light traveling through what appears to be absolutely nothing. Successfully measuring this would be direct, incontrovertible proof of the quantum vacuum's active structure. So why go to all this trouble? Because this fundamental research might be the key to unlocking the secrets of the cosmos on the largest scales. The energy inherent in this quantum vacuum could be the driving force behind one of the greatest mysteries in all of science, dark energy. This is the mysterious repulsive force causing the expansion of the universe to accelerate. When theorists try to calculate the amount of energy the quantum vacuum should contain, based on our current understanding of particle physics, the number they get is wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the history of science. This colossal discrepancy tells us that something is profoundly wrong with our understanding, that a deep truth is waiting to be discovered in the chaos of the quantum foam. By directly probing and measuring the vacuum's properties in the lab, we might finally find the missing piece of physics that reconciles the quantum world with the cosmic scale, potentially leading to a revolution in our understanding of reality, as significant as the theories of relativity or quantum mechanics themselves. We are not just studying empty space, we are testing the foundational principles of the universe, one impossibly precise measurement at a time. Yet if the quantum foam represents the hidden chaos at the smallest scales, our next discovery reveals a profound and unsettling absence on a truly colossal scale. For decades, the existence of dark matter has been a cornerstone of modern cosmology, the invisible glue we believed was essential for holding every galaxy together. But right now, our telescopes are focused on a handful of galactic anomalies that defy this fundamental rule, islands in the cosmos that appear to be missing this dark material entirely. The most famous of these, a ghostly galaxy known as NGC 1052DF2, is not a relic from the past. It is a present-day crisis for our models of the universe, and the investigation into its true nature is more intense than ever. When Yale astronomer Pieter van Dokkum and his team first studied this galaxy with the Dragonfly telephoto array, they knew they were looking at something peculiar. DF2 is what's known as an ultra-diffuse galaxy. It's as wide as our Milky Way but contains only about 1% of the stars, making it incredibly faint and see-through. This transparency was the key to unlocking its mystery. Because you can literally see straight through it, astronomers could measure the motions of its star clusters and globular clusters with incredible precision. The laws of gravity dictated by Newton and Einstein are clear. The speed at which these clusters orbit the galaxy's center should be dictated by the total mass pulling on them, both visible and dark. To the team's astonishment, the clusters in DF2 were moving surprisingly slowly. When they calculated the mass required to produce such sluggish orbits, it aligned almost perfectly with the mass of all the visible stars and gas. There was no room left for dark matter. It was as if they had found a car speeding down a highway with its engine removed, gliding along by some unknown means. This finding was so revolutionary that it sparked immediate and fierce debate within the astronomy community. The primary challenge was to confirm the distance to DF2, as this is critical for calculating its mass. If the galaxy were much closer to us than initially thought, its stars would be intrinsically dimmer, meaning there would be less visible mass present, and the observed motions could once again be explained by the presence of dark matter. This kicked off a frantic race to measure its distance using the Hubble Space Telescope by studying the properties of its stars. The latest and most precise measurements have strongly supported the original distance, and by extension, the conclusion that this galaxy is severely lacking in dark matter. The evidence is so compelling that other similar galaxies, like DF4, have since been identified, strengthening the case that DF2 is not a fluke but a member of a new, bizarre class of celestial object. The existence of such galaxies creates a fascinating paradox. If dark matter is the essential scaffolding upon which all galaxies are built, how did DF2 form without it? One leading theory suggests it was born from a very different process. During a chaotic galactic collision or a near miss between two large galaxies, a torrent of gas could have been pulled out into intergalactic space. In this new, quiet environment, far from the gravitational influence of dark matter, the gas could have collapsed under its own gravity to form stars, creating a galaxy made purely of ordinary, visible matter. It would be a cosmic orphan, a galaxy born from the debris of a violent encounter rather than from the slow accumulation of dark matter. Another, even more mind-bending idea is that dark matter and ordinary matter can, under certain rare conditions, be separated during galaxy formation, though the mechanics of how this could happen remain entirely speculative. This ongoing investigation forces us to confront a critical question. What truly holds a galaxy like this together? Without the immense gravitational anchor of a dark matter halo, the stars in DF2 should be flying apart, yet they remain tenuously bound. The answer might lie in its unique and serene environment. DF2 resides near a massive elliptical galaxy called NGC 1052, which sits in the center of its own dense halo of dark matter. It's possible that the larger galaxy's gravitational field is providing a stabilizing influence, acting as a cosmic shepherd that helps keep the fragile star system intact. This would make DF2 a satellite in a very literal sense, its structure dependent on an external force rather than an internal one. The implications of these dark matter-deficient galaxies are enormous. For one, they provide some of the strongest evidence that dark matter is real and not a misunderstanding of our laws of gravity. If our theory of gravity were wrong and needed to be modified, as some have proposed, then that modified theory should apply universally and would predict the motions in DF2 just as well as in any other galaxy. The fact that it doesn't suggest that dark matter is a tangible substance that can be present or absent, separate from the visible stuff of stars and planets. Furthermore, their existence proves that galaxy formation is a far more complex and diverse process than our standard models allow. The universe, it seems, has found another way to build an island of stars, and by studying these strange outliers, we are not just learning about exceptions to the rule, we are fundamentally rewriting the rulebook on how galaxies are born and live their lives. But if our own solar system can provide such profound mysteries, we need only look to its very edge to find one of the most compelling and active puzzles in planetary science today. Far beyond the orbit of Neptune, in the cold, dark reaches of space, lies a vast reservoir of icy worldlets known as the Kuiper Belt. This is the solar system's final frontier, and right now, our most powerful surveys are mapping it in unprecedented detail, only to confirm something deeply strange. The belt doesn't just gradually fade away. It simply ends. This is the mystery of the Kuiper Cliff, a sudden and dramatic drop-off in the number of objects that has astronomers scrambling for an explanation, with theories ranging from the violent history of our early solar system to the existence of a hidden world we have yet to lay eyes on. To understand why this cliff is so baffling, we need to picture what we expected to find. The Kuiper Belt is often thought of as a much larger and more distant cousin to the asteroid belt between Mars and Jupiter. It's a donut-shaped ring populated by countless icy bodies, including dwarf planets like Pluto, Haumea, and Makemake. Based on our models of how the solar system formed from a swirling protoplanetary disk, we anticipated that the number of objects in this belt would slowly and steadily decrease the farther out you go, eventually blending into the even more distant Oort cloud. It should be a gentle slope into nothingness, but that is not what the data shows. Instead, at a distance of around 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun, the population of Kuiper Belt objects, or KBO, plummets. It's as if you were walking through a densely packed forest and suddenly stepped over an invisible line onto barren, empty ground. The sheer abruptness of this boundary suggests that something dramatic happened here or is still happening that swept this region clean. Uncovering this cliff is a painstaking, real-time endeavor that relies on the world's most powerful wide-field telescopes. The Subaru telescope on Mauna Kea in Hawaii, with its massive mirror and incredibly wide field of view, is a powerhouse in this search. Night after night, its camera takes sequential images of the same patches of sky far beyond Neptune. Astronomers then use sophisticated software to scan these images for the telltale sign of a KBO, a faint point of light that has moved just slightly against the backdrop of fixed stars between exposures. Each discovery is plotted on a map of the outer solar system, and over years of this meticulous work, the map has revealed a stark and empty frontier. Other facilities like the Victor M. Blanco telescope in Chile and the upcoming Vera C. Rubin Observatory are accelerating this census, their digital eyes scanning the darkness and confirming the cliff's existence with ever greater statistical certainty. This isn't a single observation, it's a growing body of evidence that is actively being gathered and analyzed, a frontier being mapped in real time. So what could have created this stark boundary? The leading natural explanation takes us back to the solar system's violent infancy, a period known as the Late Heavy Bombardment. The prevailing theory, called the Nice Model, suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. They migrated outward, their gravitational dance destabilizing the primordial disk of planetesimals. In this chaotic reshuffling, Neptune is thought to have plowed outward into the dense Kuiper belt, its gravity scattering countless objects inward toward the Sun or outward into distant orbits. This migration could have truncated the belt, carving out its inner edge and leaving a sharp cutoff in its wake. It's a compelling story that fits much of what we see, but some astronomers question whether planetary migration alone could have created such a precisely defined and empty cliff. This is where the more sensational and tantalizing theory enters the picture, Planet 9. The hypothesis, developed by astronomers Konstantin Batygin and Mike Brown, proposes that the gravitational influence of a large, undiscovered planet, perhaps 5 to 10 times the mass of Earth orbiting hundreds of astronomical units from the Sun, could be the architect of this emptiness. The gravity of such a massive world could have shepherded the distant Kuiper belt, either ejecting objects from the solar system entirely or pulling them into orbits so eccentric and tilted that they evade our current surveys. The Planet 9 theory was initially proposed to explain the peculiar, clustered orbits of a handful of extreme trans-Neptunian objects, but its potential influence could extend to explaining the Kuiper cliff as well, acting as a gravitational barrier that defines the edge of the populated solar system. The hunt for this hypothetical planet is now one of the most thrilling chases in modern astronomy. Teams are using the Subaru telescope to conduct a methodical, years-long survey of the most likely swaths of sky where Planet 9 could be hiding. The challenge is immense. It would be incredibly faint, moving incredibly slowly against the stars, and its orbit could take it through a vast volume of space. Finding it is like searching for a single, dimly lit needle in a haystack the size of a continent. Yet, with every month of observation that passes without a discovery, the possible hiding places are narrowed down. We are actively closing the net, and the potential discovery would be a monumental event, rewriting astronomy textbooks and redefining our solar system's family portrait. Whether the answer is a dramatic ancient migration or a hidden modern giant, the investigation into the Kuiper cliff is far more than an academic exercise. It is a direct probe into the formation and evolution of our planetary home. The objects in the Kuiper belt are pristine fossils from the dawn of the solar system, and their distribution holds the key to understanding the gravitational forces that shaped everything we see today. Each new KBO discovered, each precise orbital measurement made, is another piece of the puzzle. We are not just looking at a static edge, we are witnessing the ongoing legacy of the solar system's most dynamic era, a story written in ice and darkness that we are only now learning to read. But for all the mysteries lurking in our own cosmic backyard, Some of the most profound questions in physics lead us to the very edge of theoretical possibility, to a concept so strange it inverts our understanding of reality itself. We are venturing into the realm of white holes, a controversial and spectacular mathematical possibility that some scientists are actively hunting for in our universe right now. To grasp what a white hole is, we must first consider its dark twin, the black hole. A black hole is defined by its event horizon, a point of no return where gravity is so intense that nothing, not even light, can escape its pull. It is the ultimate cosmic vacuum cleaner. A white hole, by its very definition, is the exact opposite. If a black hole is a one-way street into oblivion, a white hole is a one-way street out of it. It is a region of space-time from which matter and energy can only erupt, never to return. Nothing can enter a white hole. It can only spew out radiation and particles in a violent, continuous outburst. The mathematics of Einstein's theory of general relativity are beautifully symmetric, and they allow for this solution. A white hole is essentially a black hole running in reverse, a cosmic fountain of creation that eternally pours its contents into the universe. The immediate and obvious question is, how could such a thing ever form? Black holes are born from the gravitational collapse of massive stars, a process we have observed. There is no known physical process that could create a white hole. They are considered by most physicists to be mathematical curiosities rather than actual astrophysical objects. However, this hasn't stopped a dedicated group of theorists and observers from pursuing the idea. Their search is based on a key prediction. If a white hole did exist, it wouldn't be quiet. It would be one of the most energetic and violent events in the cosmos. As matter attempted to fall back into it, it would collide with the torrent of material being expelled, creating a titanic shockwave that would likely manifest as an incredibly powerful, high-energy explosion of gamma rays. Some researchers have proposed that the mysterious origins of certain long gamma ray bursts, the most powerful explosion since the Big Bang, or even some ultra-high-energy cosmic rays could potentially be explained by a white hole event. These are the signatures astronomers are now sifting through mountains of data to find, a needle in a haystack search for an event that, by all standard accounts, shouldn't be possible. The hunt is focused on several fronts. Teams are analyzing data from gamma-ray observatories like the Fermi Gamma Ray Space Telescope and the SWIFT satellite, looking for bursts that have a peculiar energy signature or a strange afterglow that doesn't fit the typical profile of a collapsing star or merging neutron stars. Others are looking at the centers of certain ancient, quiet galaxies, theorizing that a white hole could potentially masquerade as a quasar that is somehow operating in reverse, expelling material instead of consuming it. There is even a fascinating, though highly speculative, connection to the mystery of dark matter. Some theories suggest that the primordial universe could have created miniature white holes in the instant after the Big Bang, and that these objects, often called Planck stars, could have since evaporated, leaving behind a stable relic that constitutes the invisible dark matter we detect today. This idea pushes the boundaries of cosmology, attempting to link the infinitely large with the infinitely small. Ultimately, the search for white holes is a testament to the power of human curiosity. It is the process of taking a beautiful, symmetric equation and asking the daring question, but what if it's real? Even if the search proves futile and white holes remain confined to the pages of theoretical physics, the effort is far from wasted. The process of looking for something so profoundly strange forces us to refine our instruments, question our assumptions, and consider our universe from a completely inverted perspective. It reminds us that the cosmos is governed by rules that often defy our intuition, and that the final chapter on what is and is not possible in our universe is still being written, one impossible idea at a time. Yet as we push the boundaries of our cosmic models, we are confronted with a discrepancy so fundamental it threatens to unravel our entire understanding of the universe's evolution. This is the Hubble tension, a growing and deeply unsettling problem in modern cosmology that is not getting better with more data, but worse. Right now, the most powerful telescopes ever built are delivering measurements that directly contradict each other, creating a crisis that has physicists considering the need for a complete rewrite of the rules governing reality. The heart of the problem lies in pinning down a single, crucial number, the Hubble constant. This value represents the current rate at which the universe is expanding, the speed at which galaxies are rushing away from us. For decades, astronomers have pursued two primary, independent methods to measure this number, confident they would eventually converge on a single, universal truth. Instead, they have diverged, and the gap between them has only widened into a chasm that can no longer be ignored. This isn't a small margin of error. It is a full-blown contradiction playing out in real time across observatories around the world. The first method builds a cosmic distance ladder, a step-by-step chain of measurements that starts in our own galactic neighborhood. Astronomers use pulsating stars called Cepheid variables and cataclysmic stellar explosions known as Type 1, a supernova, as standard candles. Because we understand their intrinsic brightness, we can measure how bright they appear from Earth and precisely calculate their distance. By also measuring the redshift of the galaxies hosting these events, how much their light is stretched by the expansion of space, we can chart the expansion rate locally. This painstaking work, heavily refined by the Hubble Space Telescope, gives us a very precise value for the Hubble constant. The latest results from this method suggest the universe is expanding at about 73 kilometers per second per megaparsec. This means that for every additional megaparsec of distance, a distance of about 3.26 million light-years, a galaxy is moving away from us 73 kilometers per second faster. The second method takes a completely different approach, looking back to the very beginning of the universe. It uses the detailed snapshot of the infant cosmos provided by the Planck satellite's map of the cosmic microwave background, the leftover radiation from the Big Bang. This ancient light reveals the precise conditions of the early universe. By plugging these measurements into the standard model of cosmology, the lambda cold dark matter model, and pressing play, we can mathematically fast-forward the universe's evolution 13.8 billion years to predict what the expansion rate should be today. This method is incredibly powerful and self-consistent, but it yields a different answer, approximately 67 kilometers per second per megaparsec. The difference of about 6 kilometers per second might seem small, but the precision of each measurement is so high that the chance this is a simple error is less than 1 in a million. We are not just arguing about numbers, we are staring at two completely different stories of the universe's expansion, both backed by ironclad evidence. This discrepancy has set off a frantic global effort to find the flaw. Is there an error in the cosmic distance ladder? Teams are now using the James Webb Space Telescope to re-observe the same Cepheid variables Hubble studied, its superior infrared vision peering through cosmic dust to confirm or correct the stellar distances with unprecedented accuracy. Others are searching for new, even more reliable standard candles to build a better ladder. Conversely, are we misreading the cosmic microwave background? New generations of ground-based telescopes are creating even more detailed maps of this ancient light, checking for any systematic errors in the Planck data or subtle signs of physics we might have missed. As these observational campaigns continue, the possibility grows that the error lies not in our measurements, but in our model itself. The standard model of cosmology might be incomplete. This realization has sparked a thrilling explosion of theoretical work, with physicists proposing fascinating new ideas that were once confined to the fringe. Perhaps dark energy, the force accelerating the expansion, is not a constant as we thought, but an evolving energy field that has changed strength over cosmic history. Maybe dark matter possesses unknown properties that allow it to interact with itself or with light in subtle ways that alter the expansion history. Some have even proposed the existence of a new, fourth type of neutrino or other exotic particles that would have flooded the early universe and altered its evolution. The most radical suggestions involve modifications to Einstein's theory of gravity itself on the largest cosmic scales. The Hubble tension is more than an academic debate. It is a live, active scientific frontier. Every new observation, every refined dataset adds another piece to this puzzle. We are witnessing the scientific process at its most raw and exciting, where a fundamental pillar of our understanding is being stress-tested. Whether the solution is a hidden error, a new particle, or a revolution in physics, resolving the Hubble tension will inevitably lead us to a deeper, richer, and undoubtedly stranger understanding of the cosmos we call home. Just when we thought we had catalogued the universe's strangest structures, our telescopes revealed something that defies all existing categories. Enormous rings of radio energy so vast they could easily swallow entire galaxies, appearing out of nowhere and baffling every astronomer who studies them. These are odd radio circles, or ORCs, and their discovery is so fresh that the ink is barely dry on the scientific papers trying to describe them. Right now, as we speak, these ghostly halos are drifting in the depths of space, and the global effort to understand what they are represents one of the most exciting and open cases in modern astronomy. The story begins with the Australian Square Kilometre Array Pathfinder, or a SKAP, a powerful new radio telescope designed to map the sky with incredible speed and sensitivity. While surveying the universe for more common radio sources, it began picking up these perfect circular rings of diffuse radio emission. They didn't correspond to any known objects in optical catalogues, they were just there. Giant celestial smoke rings hanging in the void. Their sheer size is what makes them so difficult to comprehend. A typical ORC can span over 1 million light-years across, meaning light would take that long to travel from one side to the other. To put that in perspective, our entire Milky Way galaxy is a mere 100,000 light-years wide. These structures are so enormous that they could easily enclose multiple galaxies within their boundaries, like a soap bubble surrounding a few scattered pebbles. The immediate challenge was figuring out what we were even looking at. The first step in any astronomical detective story is to look at the object in different wavelengths of light. So that's precisely what teams around the world did. They pointed optical telescopes like the Hubble and, more recently, the James Webb Space Telescope toward the coordinates of these radio circles. In some cases, they found a galaxy sitting neatly at the very center of the ring, often a massive elliptical galaxy. This was a crucial clue, suggesting the phenomenon was somehow linked to activity within that central galaxy. They also used X-ray telescopes like Chandra to search for high-energy signatures, and other radio observatories to study the polarization of the radio waves, which can tell us about magnetic fields. The multi-wavelength portrait that is emerging is of a complex, energetic event, but the picture is still frustratingly blurry. With each new observation, a list of potential explanations has grown, each more fascinating than the last. One leading theory posits that these are the aftermath of a titanic explosion at the galaxy's core. Perhaps a merger of two supermassive black holes sent a colossal shockwave screaming out into intergalactic space. This expanding shell of energy would heat up tenuous gas and energize particles, causing them to emit radio waves in the vast spherical pattern we observe. Another compelling idea connects them to a phenomenon known as a starburst wind. If a galaxy underwent a period of incredibly intense star formation, the combined effect of countless supernovae could blow a gigantic galactic wind, carving out a cavity in the surrounding gas and leaving a radio-bright shell at its edge. Yet, some of their properties are so unusual that they have prompted even more exotic suggestions. Could an ORC be the throat of a wormhole, a tunnel in spacetime predicted by Einstein's equations but never observed? Or perhaps it is the imprint of a jet from a supermassive black hole that has precessed or wobbled over millions of years, effectively painting a giant circle on the sky with its energy. The most speculative theory wonders if we are seeing the signature of a technology belonging to a Type 3 Kardashev civilization. Though most astronomers consider this the least likely possibility, it speaks to the sheer profundity of the mystery. The investigation is accelerating because we are finding more of them. What started as a handful of curious anomalies has grown into a recognized class of object, with new ORCs being identified in radio surveys from South Africa's Meerkat telescope and other facilities. Each new discovery provides another data point, helping astronomers to classify different types and piece together their life cycle. The key to solving the puzzle will likely come from next-generation instruments like the full square kilometer array, which will have the resolution to peer into the fine structure of these rings and perhaps catch one in the very act of formation. For now, these mysterious circles remain one of the sky's most captivating new riddles, a powerful reminder that no matter how much we map the cosmos, it is always ready to reveal a new wonder that challenges everything we think we know. And just as we grapple with the Hubble tension, a discrepancy in the universe's present expansion, an even more profound and unsettling mystery haunts us from the very dawn of time, etched into the first light of creation itself. This is the axis of evil, a cosmological anomaly so named because it challenges one of the most sacred principles in all of science, the idea that the universe on the largest scales is the same in every direction. This isn't about a strange object or a fleeting burst. It's about the fundamental architecture of reality, and right now, the most precise map of the infant universe we have continues to show this bizarre, perhaps impossible, alignment. To understand why this is so deeply troubling, we have to go back to the cosmic microwave background, or CMB. This is the leftover glow from the Big Bang, a snapshot of the universe when it was just 380,000 years old, now cooled to a faint microwave whisper that permeates all of space. The standard model of cosmology rests on the assumption that this early universe was almost perfectly smooth and isotropic, meaning it should look the same in every direction we observe. Tiny, random fluctuations in this background are the seeds from which all galaxies, stars, and planets would eventually grow. When scientists created the first detailed, full-sky map of this radiation with the Oumuamua satellite, they expected to see a beautiful, random pattern of hot and cold spots, a cosmic Jackson Pollock painting. But as they analyzed the data, they found something that sent a shiver through the astrophysics community. The fluctuations weren't completely random. They appeared to be aligned or correlated along a particular axis that seems to be suspiciously related to our own solar system. It was as if the universe's blueprint had a giant, invisible arrow painted across it, and the arrow was pointing right at us. This discovery was so shocking that the scientific community initially hoped it was a fluke, an artifact of the instrument or a statistical error. Then the Planck satellite was launched. With resolution and sensitivity far surpassing Oumuamua, Planck was tasked with creating the ultimate map of the CMB, a map so precise it would either confirm the anomaly and plunge cosmology into crisis, or erase it and restore order to our understanding. The data from Planck did neither. Instead, it confirmed the anomaly with even greater confidence. The so-called axis of evil persisted. The coldest and hottest spots in the ancient sky are arranged in a way that suggests a preferred direction, a cosmic north and south that should not exist if the cosmological principle holds true. Statistically, the odds of this alignment happening by pure chance are incredibly low, on the order of 1 in 1,000. We are left with a universe that appears to have a haunting, large-scale structure that is intimately and bizarrely linked to our own minuscule place within it. So what could this mean? The explanations range from the mundane to the utterly revolutionary. The first and most hopeful possibility is that we are still being fooled. Perhaps our view of the CMB is being contaminated by something much closer to home. Dust in our own galaxy, or the gravitational influence of nearby galaxy clusters, could potentially be distorting the pristine signal from the early universe in a way that creates this illusory axis. Teams are right now using multi-wavelength data from Planck and other observatories to painstakingly model and subtract every possible foreground contaminant, and the anomalies stubbornly remain. Another fascinating, though less unsettling, idea is that the universe might be finite and have a non-trivial topology, meaning it might be shaped like a torus or have a connected, repeating structure. In such a universe, light could wrap around, and we might be seeing multiple images of the same fluctuations, creating patterns that look aligned from our specific vantage point. But if the alignment is real and fundamental, the implications are staggering. It could mean that our location in the universe is not arbitrary but special. This directly assaults the Copernican principle, the foundational idea that we do not occupy a privileged place in the cosmos. It suggests that the universe has a large-scale symmetry that is oriented relative to us, a concept that is profoundly difficult to reconcile with our models. Some theorists have even proposed that this could be a sign of a pre-Big Bang physics, an imprint from a larger multiverse that set the initial conditions for our own cosmic pocket. The axis of evil is more than just a name. It represents a fundamental threat to the core assumptions that have guided cosmology for a century. It is a mystery written in the first light of the universe, a whisper from the beginning of time that we are only now learning to hear, and it tells us that the cosmos may be far stranger and more complex than we ever dared to imagine. But if the universe is expanding in a way that creates tension in our models, and its very structure hints at a strange, preferred axis, then our next discovery suggests that this motion might not be entirely random or uniform. Imagine the entire cosmos not just expanding, but flowing, with thousands of galaxy clusters moving in a coordinated, river-like stream towards a point on the distant horizon. This is the mystery of dark flow, a controversial and potentially paradigm-shifting observation that hints at forces or structures so immense they lie beyond the edge of everything we can see. The story of dark flow begins not with visible light, but with the faint afterglow of creation itself. To detect this subtle, coordinated motion, astronomers use a brilliant technique called the kinetic Sunyaev-Zeldovich effect. Here's how it works. The cosmic microwave background is our universal reference frame, the oldest light in existence. As massive galaxy clusters move through space, the hot electrons within their gas clouds scatter this ancient light. If a cluster is moving toward us, the scattered light becomes slightly brighter and hotter. If it's moving away, the light becomes slightly dimmer and cooler. It's the astrophysical equivalent of the Doppler effect you hear when a siren changes pitch as it passes by, but applied to the faintest microwave whisper from the beginning of time. By meticulously measuring these tiny, telltale distortions in the CMB caused by the motion of thousands of clusters, we can map their velocity and direction with astonishing precision. When a team led by astronomer Alexander Kashlinsky performed this painstaking analysis using data from the Oumuamua and later the Planck satellite, they found something that defied all conventional explanation. The clusters weren't just moving randomly with the general expansion of the universe. They detected a consistent, coherent flow, a dark flow, of these massive structures all moving in the same direction at incredible speeds of nearly 1,000 kilometers per second. This isn't a small, local current. The signal has been detected in clusters billions of light-years away, suggesting the source of this pull must be unimaginably vast and powerful, and more perplexingly that it lies outside our observable horizon. This is where the mystery turns profound and deeply controversial. According to our standard cosmological models, the observable universe is meant to be isotropic and homogeneous on the largest scales. The mass distribution should be even enough that there are no gravitational gradients large enough to pull entire galaxy clusters in a single, coordinated direction. The gravitational influence of known structures like the Shapley supercluster can account for some local motion, but nothing on this scale and coherence. The existence of dark flow implies a colossal asymmetry, a gravitational pull from something so enormous that its mass warps the fabric of space-time from beyond the veil of what we can see. This suggests one of two breathtaking possibilities. The first is that the structure causing this flow is a concentration of mass on a scale we have never imagined, a supercluster or a massive void whose gravitational influence extends into our observable universe from a region that formed before the period of cosmic inflation stretched it beyond our sight. The second, and even more radical idea, is that this flow is evidence of a neighboring universe in a vast multiverse, whose gravitational tug is somehow leaking into our own cosmic bubble. Naturally, a claim this extraordinary faces intense scrutiny and debate within the scientific community. Skeptics have questioned the methodology, suggesting that the detected signal could be a subtle systematic error in how the CMB data is processed, or an incomplete subtraction of foreground emissions from our own galaxy. Other teams have performed their own analyses using different techniques and satellite data, with some confirming the anomaly and others finding no evidence for it. This lack of consensus is not a failure of science, but the very process of it working, a fierce, healthy debate played out in peer-reviewed journals and at conferences, driven by the need for irrefutable evidence. The measurements are at the very limit of our technological capabilities, dealing with signals so faint that isolating them from noise is a Herculean task. The quest for a definitive answer is now pushing our technology to its absolute limits. The next chapter in this investigation will be written by new observatories and advanced statistical techniques. The James Webb Space Telescope, while not designed for this specific measurement, is providing exquisite data on the velocities of distant galaxies, offering an independent way to check these flow patterns. Future CMB missions designed with even greater sensitivity will be able to measure the kinetic Sunyaev-Zeldovich effect with unprecedented accuracy, potentially confirming or finally ruling out dark flow once and for all. What makes this mystery so compelling is its potential to shatter our cosmological paradigm. If confirmed, dark flow would be our first empirical hint that there is a beyond to our observable universe, that our cosmic horizon is not a final boundary but merely the limit of our current vision, and that we are but a small part of a structure so grand it defies our current comprehension. We are left watching this river of galaxies, wondering where it leads and what unimaginable source is drawing everything toward it. Our journey now takes us from the grand, cosmic scale of flowing galaxies down to the thin, cold air of a neighboring world, where a tantalizing whisper has been detected, a whisper that could change everything we know about life in the universe. This is the Mars methane mystery, an ongoing scientific detective story where the prime suspect is nothing less than biology itself, and the investigation is happening in real time, under the wheels of our rovers and the watchful eyes of our orbiters. For decades, Mars has been viewed as a frigid, seemingly sterile desert, a planet where the chemistry of life ground to a halt billions of years ago. But that view was shattered by a series of startling observations. Methane, a simple gas, became the center of a firestorm of debate. On Earth, the vast majority of methane in our atmosphere is produced by biological processes by living organisms, from microbes to cows. It can also be produced abiotically through geological reactions involving water, carbon dioxide, and certain rocks like olivine. But finding it on Mars is like smelling smoke in a forest. It doesn't guarantee a fire is still burning, but it demands an immediate and thorough search for its source. The plot thickened because this Martian methane didn't behave like a steady, predictable atmospheric gas. Instead, it appeared in maddeningly sporadic spikes. The Curiosity rover, diligently sniffing the air in Gale Crater since 2012, has recorded these fugitive bursts. Its onboard instrument, the tunable laser spectrometer, has measured methane levels that occasionally soar to 10 times the background level, only to vanish almost as quickly as they appeared. These aren't subtle changes, they are dramatic plumes that appear and dissipate within a single Martian day. This intermittency is the heart of the mystery. If the methane were from a constant, slow geological seep, we would expect to see a steady, low-level presence. The fact that it spikes so violently suggests it is being released in sudden, pulsed events from one or more localized sources, and then is being rapidly destroyed by something in the Martian atmosphere. So where is it coming from? The hunt for the source has split into two compelling camps. The geological hypothesis points to a process called serpentinization. This occurs when certain minerals in volcanic rock, like olivine, interact with water deep underground. This reaction can produce methane as a byproduct. Mars has plenty of the right rocks and strong evidence of a watery past. A subsequent geological process could involve methane clathrates, cage-like structures of water ice that trap methane molecules underground. These frozen reservoirs could be destabilized by seasonal temperature changes or small seismic activity, cracking open and releasing their stored gas in sudden, explosive belches. This is a perfectly plausible, non-biological explanation that aligns with what we know about Martian geology. But the biological hypothesis is what captures the imagination and fuels the investigation. Could these methane bursts be the faint, gaseous signature of a subterranean biosphere? Deep beneath the frozen, irradiated surface, shielded from the harsh conditions above, microbial life could potentially persist. These organisms might metabolize hydrogen and carbon dioxide, producing methane as a waste product, just as their counterparts do deep within Earth's crust. A large, dormant microbial community could be periodically activated by subtle environmental shifts, leading to a burst of metabolic activity and a subsequent release of gas. It is a breathtaking possibility that we are not alone and that the proof is drifting in the Martian breeze, just waiting for us to catch it. The reason this mystery remains unsolved is that the evidence is frustratingly contradictory. While Curiosity on the ground has repeatedly detected these spikes, the Trace Gas Orbiter, a sophisticated European spacecraft circling the planet, has largely drawn a blank. Its highly sensitive instruments, designed specifically to map trace gases across the entire planet, have found the global methane background to be astonishingly low and uniform. This discrepancy is its own fascinating puzzle. It could mean that the methane Curiosity smells is incredibly localized and confined to the ground, destroyed by some unknown oxidizer in the atmosphere before it can rise and spread globally. Or it could point to a timing issue. The orbiter might simply be missing the brief, violent bursts that the rover happens to catch. This is why the research is so active and urgent. Every new Sol or Martian day, Curiosity continues its measurements, building a long-term timeline of these events. Scientists are meticulously cross-referencing these methane spikes with other data. Temperature changes, atmospheric pressure, seasonal dust storms, and even the rover's own position. The goal is to find a pattern, a trigger. Could the releases be tied to the Martian seasons, to the daily thawing of surface frost? The community is watching this data unfold in real time, with each new paper adding another piece to a puzzle that is far from complete. The resolution to this mystery may ultimately come from the next generation of rovers and the samples they are collecting. Perseverance, exploring the ancient river delta in Jezero Crater, is equipped with instruments that could potentially detect more complex organic molecules associated with life. While it doesn't have a dedicated methane sniffer like Curiosity, its overall mission to seek signs of ancient life is intrinsically linked to this puzzle. The ultimate test will be when the samples it has carefully cached are returned to Earth by a future mission. In our most advanced laboratories, we could perform analyses that are impossible on Mars, searching for isotopic fingerprints in any trapped gases. Certain ratios of carbon isotopes in methane can be a powerful biosignature, as life on Earth prefers to use the lighter carbon-12 isotope over the heavier carbon-13. If the Martian methane shows a similar preferential fingerprint, it would be the strongest evidence yet that we are not alone. Until then, the mystery persists a ghost in the atmosphere of a red planet, a tantalizing clue that we are closer than ever to answering one of humanity's oldest questions. But our journey into the bizarre now takes us from the ghostly whispers of Martian methane to a phenomenon so fundamentally strange it seems to defy the very nature of reality itself. We are entering the realm of quantum entanglement, a concept so counterintuitive that even Einstein famously described it as spooky action at a distance. For decades, this strange connection between particles has been tested in laboratories, but right now, physicists are preparing the most ambitious experiments ever conceived, aiming to stretch this quantum link across not just meters, but across vast astronomical distances, in a quest that could finally unite the worlds of the very small and the very large. To grasp why this is such a monumental endeavor, we first need to understand the core of the mystery. Quantum entanglement occurs when two particles, like photons or electrons, are created or interact in such a way that their properties become inextricably linked. They form a single, unified quantum system. The truly bizarre part is what happens when you measure one of them. Instantly, no matter how far apart they are, the other particle seems to know and assumes a corresponding state. If you measure one photon and find it spinning clockwise, its entangled partner, even if it's on the other side of the galaxy, will be found spinning counterclockwise. This connection appears to happen faster than the speed of light, which seems to violate the fundamental rules of relativity. For a century, we've known this spooky connection works across lab benches and even across cities, but the burning question has always been, does it have a limit? Is there a distance where this quantum weirdness breaks down, or does it truly bind the universe together in a web of instantaneous connection? This is where the experiments shift from the theoretical to the truly cosmic. The next generation of tests is not happening in basement labs, it's moving into space. The concept is audacious. Create a pair of entangled photons here on Earth, then beam one of them to a receiver on a satellite or even a deep space probe millions of miles away. The other photon is kept in a highly secure quantum memory bank on the ground. Scientists would then perform measurements on both particles simultaneously, checking to see if their magical correlation holds across interplanetary distances. One proposed mission, often discussed by agencies like NASA and the European Space Agency, involves using the International Space Station or a dedicated satellite as a relay node. Another, even more ambitious idea is to use the light from distant quasars as a natural random number generator to decide how to measure the particles, ensuring that any choice made is truly random and not influenced by any hidden variables, closing potential loopholes in the experiment once and for all. The motivation for pushing entanglement to these extreme limits is far more profound than simply setting a record. Physicists are hunting for something that has eluded them for a century, a theory of quantum gravity. Our two most successful theories, quantum mechanics, which explains the tiny world of particles, and general relativity, which explains the large-scale structure of spacetime, are fundamentally incompatible. Many theorists believe that the key to uniting them lies in understanding how gravity, the last holdout, interacts with the quantum world. Some models predict that the fabric of spacetime itself might have a granular, foamy nature at the smallest scales. This quantum foam could potentially disrupt the delicate entangled state over very long distances. If we were to perform a cosmic-scale entanglement experiment and suddenly find that the spooky connection fails, it would be a monumental discovery. It would be the first experimental evidence that space-time itself has a discrete structure that can decohere quantum states, providing a crucial clue for how to build a theory of quantum gravity. Conversely, if the entanglement holds perfectly across millions of miles, the implications are equally, if not more, staggering. It would provide ironclad proof that the universe is fundamentally non-local, that connectivity is a built-in feature of reality that transcends space and time. This wouldn't allow for faster-than-light communication. The correlation is random and can't be used to send a message, but it would force us to radically rethink our understanding of causality and separation. It would suggest that the universe is far more deeply interconnected than our classical intuition allows, with particles sharing a bond that exists outside of our conventional four-dimensional spacetime. This profound connectedness might even have implications for the very nature of consciousness and information in the cosmos, ideas that are already being explored at the furthest frontiers of theoretical physics. These experiments are no longer science fiction, they are in the advanced planning stages. Laboratories around the world are developing the necessary technology: ultra-stable lasers for sending photons through the atmosphere, advanced quantum repeaters to mitigate signal loss, and cryogenically cooled quantum memories that can preserve a particle state long enough for its partner to complete a journey that could take seconds or even minutes. Every technological breakthrough in quantum computing and communication brings this cosmic test closer to reality. We are on the cusp of conducting an experiment that will probe the deepest fabric of reality, an experiment that could reveal whether the universe is ultimately a collection of separate objects or an indivisible, entangled whole. The answers we find won't just rewrite physics textbooks, they will challenge our most basic perceptions of what it means to be connected in a vast and mysterious cosmos. But just as we grapple with the invisible pull of dark matter and the profound silence of the Fermi paradox, we are confronted by a missing person's case on a truly cosmic scale. This isn't about dark matter or dark energy. This is about the ordinary, everyday stuff you and I are made of: the protons, neutrons, and electrons that physicists call baryonic matter. Based on our meticulous census of the early universe, taken from the pristine cosmic microwave background, we know exactly how much of this normal matter should have been created in the Big Bang. Yet, when we add up everything we can see today, all the stars, planets, gas clouds, and dust in all the galaxies, we come up shockingly short. A third of the universe's normal matter is simply gone. This is the missing baryon problem, and right now, a global team of astronomers is closing in on the prime suspect, hunting for this lost material in the most elusive corners of the cosmos. Where do you even begin to search for something that makes up a third of all normal matter yet has remained invisible for so long? The leading hypothesis points to a vast, diffuse network of incredibly hot gas that fills the spaces between galaxies. This is the warm-hot intergalactic medium, or WIM, and it is the final frontier of the cosmic web. Imagine the universe's structure not as isolated islands of galaxies, but as a magnificent spiderweb with galaxies clustered at the intersections of its silky filaments. Theory predicts that the gravitational pull of dark matter has drawn the WIM into these filaments, heating it to temperatures between 100,000 and 10 million degrees Kelvin. Gas this hot doesn't emit visible light. It glows faintly in high-energy X-rays, which are completely blocked by Earth's atmosphere. This is why it has evaded detection for so long. It's essentially a ghostly, ultra-hot fog woven between every galaxy we see. Catching this ghost requires the most powerful X-ray eyes ever built, and the investigation is happening right now. Space-based observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton are acting as cosmic detectives, training their gaze on the most promising targets, incredibly bright and distant objects called quasars. The strategy is brilliant in its simplicity. As the intense light from a distant quasar travels billions of light years to reach us, it passes through these faint filaments of the WIM. The superheated gas in the filaments absorbs very specific wavelengths of this light, leaving behind a unique fingerprint, a series of tiny, telltale dips in the quasar's X-ray spectrum. It's like analyzing the light from a distant lighthouse through a specific kind of fog. The pattern of what's missing in the light tells you exactly what the fog is made of. Identifying these absorption lines is painstaking work, akin to finding a needle in a haystack the size of a planet, but it's how we are finally starting to bag our missing matter. The search is being dramatically aided by another incredible tool, the most sophisticated supercomputer simulations of the universe ever created. Programs like the Illustris TNG project have modeled the entire evolution of the cosmos from just after the Big Bang to the present day, and they all predict the same thing. They show the missing baryons being heated and stretched by the gravitational forces of the cosmic web, exactly into the form of the WIM, settling into the immense filaments that connect galaxy clusters. These simulations act as a treasure map, giving astronomers a much better idea of where to point their telescopes. They don't just show a random fog, they predict a specific, intricate structure, and by combining this predictive power with the real observational data from Chandra and XMM Newton, the case is being cracked wide open. Recent observations have indeed begun to successfully detect the signatures of highly ionized oxygen and other elements in these filaments, providing the first direct evidence that the WIM is real and that it contains a significant portion of the universe's long-lost ordinary matter. Solving this mystery is about far more than just completing a cosmic inventory. Finding these missing baryons is absolutely crucial for confirming our entire story of the universe's evolution. The fact that our models of the early universe so precisely predict the amount of normal matter, and that we are now finding it exactly where those models said it should be, is a resounding triumph for the standard model of cosmology. It confirms that we fundamentally understand how the universe grew from a smooth, hot soup into the complex web of structures we see today. This ongoing detective work, this meticulous piecing together of the cosmic crime scene, ensures that the foundation of modern cosmology is built not on missing evidence, but on a complete and consistent picture of everything the universe is made of, from the darkest mysteries to the very atoms that make us who we are. Yet as we search for life's building blocks in the atmosphere of Mars and the quantum connections between particles, we arrive at a world that feels at once utterly alien and strangely familiar, a place where the chemistry of life is being written in rivers of methane and an atmosphere thick with organic potential. This is Saturn's moon Titan, and right now, as it orbits the ringed planet, it is hosting a cascade of chemical processes so complex and active that it represents the most compelling laboratory for probiotic chemistry in our entire solar system. Imagine a world with a thick, hazy orange atmosphere where the sky rains liquid methane and ethane, filling great lakes and seas that dot an icy landscape. The surface temperature is a cryogenic -290 degrees Fahrenheit, cold enough that water ice is as hard as rock, and the familiar cycles of Earth evaporation, cloud formation, and precipitation are all happening, but with a completely different set of ingredients. This is the stage upon which Titan's mysterious chemistry plays out, a drama we first began to understand thanks to the Cassini-Huygens mission, which spent over 13 years studying the Saturnian system. The Huygens probe famously touched down on Titan's surface in 2005, sending back images of a terrain carved by fluid flow, with rounded icy pebbles littering a riverbed, while the Cassini orbiter used its radar to pierce the thick haze, mapping vast expanses of dark, liquid hydrocarbons in the North Polar regions. But the real magic is happening invisibly, high in the moon's nitrogen-rich atmosphere. Here, sunlight and energetic particles from Saturn's magnetosphere are constantly bombarding molecules of methane and nitrogen, providing the energy to break them apart and reassemble them into far more complex compounds. This process creates a steady drizzle of organic molecules that falls to the surface like slow-moving snow. Cassini's instruments detected a mind-boggling array of these compounds, from simple hydrocarbons like ethane and propane to benzene rings and negative ions that are the known precursors to the most complex molecules essential for life as we know it. The sheer complexity and sheer volume of this organic factory is what makes Titan so extraordinary. It's not a frozen relic but an actively evolving chemical system, creating a deep layer of organic goo on its surface that could be hundreds of meters thick in places. This ongoing analysis of Cassini's data, years after the mission ended, continues to reveal new layers of complexity. Scientists are now using sophisticated laboratory experiments on Earth, recreating Titan's cold conditions in chambers to simulate these atmospheric reactions. They shine UV light on mixtures of nitrogen and methane gas and watch as they form Tholen's sticky, complex organic polymers that give Titan its characteristic orange-brown color. These tholins are not themselves alive, but they are the kind of complex organic matter that, on the early Earth, could have been a crucial feedstock for the emergence of life. The discovery of vinyl cyanide in Titan's atmosphere was particularly thrilling, as laboratory studies suggest that this molecule could form stable, flexible membranes around microscopic cavities in Titan's methane seas, analogous to the lipid bilayers that encase living cells on Earth. While this wouldn't be life, it would represent a giant step toward the self-organization of complex chemistry, a process we call prebiotic chemistry. The next chapter in this investigation is already in advanced preparation, and it promises to be one of the most exciting planetary science missions ever attempted. NASA's Dragonfly mission is not a traditional rover. It's a nuclear-powered dual quadcopter, a drone designed to fly through Titan's thick atmosphere and low gravity, hopping from one site of interest to another. Scheduled to launch in 2028 and arrive in the mid-2030s, Dragonfly will land in the Shangri-La Dune field, a region of dark, organic sand dunes, before making its way to the Selk impact crater, where scientists believe liquid water once briefly mixed with the surface organics. Its instruments will be able to do what Cassini could not, taste the surface material directly. It will use a mass spectrometer to identify the exact composition of the complex organic molecules, search for chemical energy gradients that could potentially be exploited by a form of life, and even listen for seismic activity or cryovolcanic rumblings throughout the long Titan day. The profound implication of studying Titan's active chemistry is that it offers us a window into a pathway for life that is completely independent of water. On Earth, water is the universal solvent, the medium in which all biochemistry occurs. Titan challenges that paradigm, presenting the possibility of a biochemistry that is liquid methane-based or perhaps even occurs in a supercooled ammonia water slurry deep beneath the icy crust. By understanding the types of molecules Titan creates and how they interact, we are essentially running a massive, natural experiment in alternative biochemistries. This expands our concept of what life could be and where we might find it, not just on icy moons in our own solar system, but on the countless exoplanets that orbit other stars. Titan is not merely a frozen time capsule from the early Earth. It is a dynamic world actively writing its own chemical story, a story we are only just beginning to read, and one that may forever change our understanding of life's potential in the cosmos. Now, let's rewind the clock to a mystery that began not with a bang, but with a whisper, a tiny, persistent deviation in the paths of two of humanity's most intrepid explorers. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were trailblazers, the first to journey through the asteroid belt and the first to make close observations of Jupiter and Saturn. But long after they completed their primary missions and fell silent, they left behind a puzzle that would captivate physicists for decades, As these twin probes ventured into the deep black, navigators tracking their radio signals noticed something extraordinarily strange. Both spacecraft were experiencing a minuscule but constant sunward acceleration, a tiny pullback toward the inner solar system that wasn't predicted by any of our models of gravitational forces. This was the Pioneer anomaly, a deviation so small it amounted to less than a billionth of the gravity we feel at Earth's surface, but it was there, consistent and unexplained, a ghost in the machine of celestial mechanics. For years, this unaccounted-for tug was a major headache for scientists. The most tantalizing possibility was that we were seeing the first hint of a flaw in our understanding of gravity itself. Perhaps Einstein's theory of general relativity needed a slight modification at the extremely weak acceleration levels experienced in the outer solar system. Some theorists proposed new physical models like modified Newtonian dynamics, or MOND, which suggested that the laws of gravity behaved differently at very low accelerations. This idea was hugely exciting because it could potentially also explain the rotation curves of galaxies without the need for dark matter. The Pioneer anomaly became a beacon for those looking to challenge the foundations of physics, a data point that seemed to point toward a revolution. But science has a way of grounding even the most exciting mysteries, often in the most mundane of details. The real breakthrough in solving the Pioneer puzzle didn't come from a new theory of everything, but from a painstaking, years-long forensic investigation into the spacecraft themselves. Teams of researchers, including the original mission engineers, dove into old design documents and blueprints stored in musty archives. They built sophisticated thermal models of the probes, and a critical clue emerged. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, which produced a significant amount of heat. This heat was emitted from the craft's central body. However, the main antenna dish used for communicating with Earth was mounted on the front, pointing back toward the Sun and Earth. The new models revealed that this heat was not radiating away from the spacecraft symmetrically. A slightly larger fraction of this thermal radiation was being emitted from the back of the craft, away from the antenna. According to the simple principle of conservation of momentum, every photon carries a tiny amount of momentum. This anisotropic or lopsided heat loss was acting like a very weak photon rocket, gently but constantly pushing the spacecraft back toward the Sun, perfectly accounting for the observed anomaly. It was a brilliant piece of detective work, proving that the answer wasn't in the stars but in the engineering. Yet, the story doesn't end there. The case was officially closed for many, but the lessons learned are actively shaping science today. The realization that something as seemingly insignificant as heat radiating from a spacecraft's electrical systems could have such a measurable effect on its trajectory has fundamentally changed how we design and navigate deep space missions. Engineers now meticulously model the thermal properties of every component, accounting for this thermal recoil force in their trajectory calculations for missions like New Horizons as it flew past Pluto and the Voyagers as they venture into interstellar space. This ensures that the navigation for these billion-dollar missions is as precise as humanly possible, a direct legacy of the Pioneer puzzle. Furthermore, the tiny discrepancy that wasn't a new physics revelation has ironically become a powerful tool for testing new physics. By providing such a precise measurement of an unexpected acceleration, it set an incredibly high bar for any proposed modification to gravity. Any new theory must now not only explain the galactic rotation curves, but also not predict an anomaly as large as the one seen by Pioneer, which we now know was instrumental. The ongoing analysis of the vast dataset from those missions continues to be a benchmark, a constant in a sea of variables against which we can test the most exotic ideas. So while the Pioneer anomaly itself was solved, its legacy is a permanent reminder of the incredible precision of modern science and the importance of questioning everything, from the laws of the universe right down to the way heat escapes from a silent, drifting probe. But if the mysteries of Titan's chemistry and the solved pioneer anomaly show us how we grapple with the known, our final bizarre event forces us to confront the very limits of knowledge itself. It is a puzzle so profound that its resolution could either shatter our understanding of reality or finally unify it, and it is happening right now not in observatories, but in the chalk-dusty halls of theoretical physics departments around the world. This is the black hole information paradox, and the frantic search for its solution is pushing human thought into realms once considered purely philosophical. To grasp why this is such a monumental problem, you have to understand two fundamental pillars of modern physics, and the fact that they are currently at war with each other over what happens to a book or a person that falls into a black hole. The first pillar is quantum mechanics, which contains an absolute, unbreakable rule: information cannot be destroyed. Information, in this sense, isn't just words on a page. It is the complete quantum state of every particle that makes up that object, its spin, its charge, its position. The theory states that if you could somehow reverse time and track every particle, you could always, in principle, reconstruct that book or that person perfectly from the scattered debris. The information is forever conserved, just scrambled. The second pillar is general relativity, which describes black holes with terrifying simplicity. Once something crosses the event horizon, it is gone forever from our universe. The black hole's only defining features, according to this theory, are its mass, its electric charge, and its spin. It doesn't matter if you throw in a perfect diamond, a supercomputer, or a library of every book ever written. The black hole will consume them all and reveal nothing about what it ate. It is the ultimate eraser, so here lies the paradox. Quantum mechanics says the information must be preserved, but general relativity says it is irrevocably lost. Both theories are spectacularly successful in their own domains, but they cannot both be right about this. For decades, the prevailing wisdom came from Stephen Hawking. He calculated that black holes are not entirely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles now called Hawking radiation. This was a revolutionary idea, but it made the paradox worse. Hawking showed that this radiation is purely thermal, it's random noise, like the static from an old television. It carries no information whatsoever about what fell in. Therefore, when the black hole finally evaporates completely, all the information it ever swallowed would vanish from the universe with it, violating the core tenet of quantum mechanics. Hawking famously argued that this meant quantum mechanics had to be modified, a bet he eventually lost, but in doing so, he framed one of the most important problems in physics. The quest to resolve this is where the story becomes electrifyingly current. The most promising avenue of research right now is rooted in the holographic principle, a concept that sounds like it's straight out of science fiction. It proposes that our three-dimensional reality, including everything that falls into a black hole, might actually be encoded on a two-dimensional surface surrounding it, like a cosmic DVD where a three-dimensional movie is stored on a flat disk. The information never actually falls into the three-dimensional hole. It is smeared and stored on the event horizon itself. Then, as the black hole evaporates and emits Hawking radiation, that radiation is not random. It subtly interacts with this encoded information on the horizon, and through an incredibly complex process of quantum entanglement, the information is gradually leaked back out into the universe, imprinted onto the escaping radiation. It would be like burning a book and having the smoke particles reassemble themselves into a perfect copy of the original text in the cloud. An unimaginable scramble, but a preservation nonetheless. Proving this is the work of a generation of physicists using the most advanced tools of quantum gravity, including string theory and its derivatives. Researchers like Stanford's Leonard Susskind have been at the forefront, developing mathematical models to show how this information transfer could work without violating other physical laws. The calculations are fiendishly complex, dealing with the quantum entanglement of countless particles, but recent papers have claimed major breakthroughs in demonstrating that Hawking radiation can indeed be purified and carry information. This isn't just abstract math, it has tangible implications. If information can escape a black hole, it means there are no true firewalls. The idea that the event horizon is a wall of destructive energy waiting to incinerate an astronaut falling in. Instead, the journey might be uneventful, but your information would remain projected on the boundary of the hole for all eternity, a ghostly testament to your existence. The resolution of this paradox is about more than just black holes. It is a direct probe into the nature of reality and the fundamental laws that govern it. Right now, this is not a settled debate. Labs are not running physical experiments, but conferences are buzzing with heated arguments over the latest mathematical proofs. The development of quantum computers is also offering a new path. Some scientists propose simulating a simplified, holographic version of a black hole in a quantum circuit to watch how information behaves. Solving the information paradox would be one of the greatest intellectual achievements in history, a triumph that would seamlessly weave together the worlds of the very large and the very small, finally giving us a complete and unified vision of how our universe truly works. And finally, we arrive at a mystery that takes us right back to the very beginning, to the first few minutes of existence when the entire universe was a searingly hot nuclear furnace, forging the first and simplest elements. The theory of Big Bang nucleosynthesis is one of the crowning achievements of modern cosmology. It precisely predicts the amounts of hydrogen and helium we see throughout the cosmos, a stunning confirmation that we understand the universe's first moments. But this elegant story has a single, glaring flaw, an inconsistency that has stubbornly refused to be solved for decades. It's known as the cosmological lithium problem, and it is an active, persistent error in the cosmic ledger that astronomers and physicists are still trying to balance today. The calculations are incredibly precise. In the first 20 minutes after the Big Bang, the universe cooled from an impossible heat to a temperature where protons and neutrons could begin to fuse. This primordial cauldron, often called the first nuclear reactor, should have produced specific amounts of the light elements, about 75% hydrogen, 25% helium, and a tiny trace amount of lithium. For hydrogen and helium, the predictions match the observed abundances in the oldest regions of the universe perfectly, but for lithium, something is very wrong. The models tell us there should be about 3 times as much lithium-7, the main isotope, as we actually find when we look at the oldest stars in our galaxy. It's not a small oversight, it's a deficit of a few 100%, a clear signal that our understanding of this foundational period is somehow incomplete. To measure these ancient abundances, astronomers turn to time machines, the oldest stars in the halo of our Milky Way. These population 2 stars, as they're known, are metal-poor, meaning they formed from gas that had been scarcely polluted by later generations of stars. They are the pristine fossils of the early universe, and by pointing our most powerful spectrographs at them, we can dissect their light. The technique is called spectroscopy. It allows scientists to spread a star's light into a rainbow of colors and look for very specific dark lines where atoms in the star's atmosphere have absorbed light. Each element has its own unique fingerprint of lines. By measuring the depth and width of the lithium absorption line in these ancient stars, we get a direct reading of how much lithium was present when they formed. Surveys like the ongoing Gala survey are doing this for tens of thousands of stars, and the result is unanimous and clear. The lithium abundance is not only lower than predicted, it is incredibly uniform across these ancient stars, suggesting the problem isn't with the stars themselves, but with the initial ingredients they were made from. So where did the lithium go, or was it never made in the first place? The investigation is proceeding on 2 main fronts. The first possibility is that our nuclear physics is slightly off. The rates of the specific nuclear reactions that produced lithium in the early universe are notoriously difficult to measure in laboratories here on Earth. Perhaps a reaction we thought was slow is actually faster, or vice versa, altering the final yield. Teams are constantly refining these experiments, using particle accelerators to recreate the conditions of the infant cosmos, but so far, no revised cross-section has managed to completely resolve the discrepancy. It's like having a perfect recipe for a cake but discovering your teaspoon measure was incorrectly sized all along, yet even after calibrating it, you're still short one key ingredient. The second possibility involves stellar processes. Could these ancient stars themselves be destroying the lithium? It's a compelling idea. As stars age and their interiors circulate, surface material can be dragged down into hotter regions where lithium is easily fused into heavier elements and destroyed. If this mixing is more efficient than we currently model, it could have gradually depleted the lithium in the atmospheres of these stars over billions of years, hiding the true primordial abundance from our view. However, the remarkable consistency of the lithium measurement in stars of different temperatures and ages poses a serious challenge to this idea. It would require an astonishingly uniform process of depletion across a vast population of diverse stars, which many astronomers find difficult to accept. This leaves us with the most thrilling possibility of all, that the lithium problem is a direct hint of new physics operating in the early universe. Perhaps an unknown particle, like a certain type of dark matter, was present and interacted with the nuclear soup, altering the reaction pathways. Or maybe the fundamental constants of nature, like the strength of the gravitational force, were slightly different in that first violent minute, just enough to tweak the outcome. These are not wild guesses, they are serious proposals published in leading physics journals, showing just how profound this puzzle is. A tiny error in our count of the universe's lightest metal could be the thread that, when pulled, unravels a much larger and more exciting tapestry of discovery, forcing us to rewrite the very first chapter of our cosmic history. So as we bring our tour of these 25 cosmic enigmas to a close, let's take a moment to just let that all sink in. From the silent, drifting rogue planets to the patterned screams of fast radio bursts, from the ghostly circles in the radio sky to the missing matter hiding in intergalactic space. We have journeyed through a universe that is not a static, distant painting, but a living, breathing, and deeply mysterious reality. Every single one of these events is unfolding right now, a constant reminder that the cosmos is not a solved puzzle, but an ongoing, dynamic story where we are turning the pages in real time. What ties all these phenomena together is not a single answer, but a single question. What else is out there? They demonstrate that for every mystery we solve, like the Pioneer anomaly, a dozen more spring up to take its place. The Hubble tension challenges the very rate of the universe's expansion. The axis of evil questions the fundamental symmetry of reality, and the search for answers to the Fermi paradox and the black hole information paradox are pushing the very boundaries of human thought. This isn't a sign that science is failing. It's the thrilling sound of science working, of our understanding stretching and growing to encompass a reality far stranger and more wonderful than we ever imagined. This golden age of discovery is powered by you. Your curiosity fuels the missions and the research. The next time you look up at a star like Betelgeuse, remember that telescopes across the globe are watching it with you. The next time you hear about a new interstellar visitor, know that observatories are already tracking its path. You can be a part of this. Follow the ongoing work of the James Webb Space Telescope as it peers into the atmospheres of exoplanets. Keep an eye on the Dragonfly mission as it prepares to fly on Titan. Read about the latest findings from the Event Horizon Telescope as it images more black holes. The data is flowing in faster than ever, and every new observation has the potential to rewrite a chapter in our cosmic story. We want to hear from you on this journey. Which of these 25 bizarre events captured your imagination the most? Does the great silence of the Fermi paradox make you wonder, or does the quantum connection of entanglement spark your sense of wonder? Is it the potential for life on Mars or Titan that excites you, or the mind-bending architecture of the cosmic web? Share your thoughts and your favorite cosmic mystery down in the comments below. Let's have a conversation about the incredible universe we all get to explore. If this journey through the bizarre and wonderful has left you wanting more, you're in the right place. We are dedicated to bringing you the latest, most fascinating discoveries from the frontiers of space and science. Make sure to subscribe and hit the notification bell so you don't miss our next adventure into the unknown. The universe is vast, mysterious, and always full of surprises. Let's continue to explore